In 2016, engineers installed a kilometer-long solar pavement on a public road in Normandy, France. Within 3 years, sustained vehicular loads caused severe cracking and delamination, halving the power output annually until the project was ultimately abandoned. A year later, a similar modular solar highway was constructed on the Jinan Expressway in China. Under the complex dynamic loading of heavy highway traffic, the structure suffered widespread mechanical failure in just 8 months. But these were not just isolated geographical anomalies. They failed because the engineers treated the road surface primarily as flat electronics, rather than active, load-bearing structural elements. Solving this requires abandoning the concept of merely paving over solar cells. We have to engineer a dual-layer pavement from the ground up, optimizing the surface geometry to survive mechanical stress, and engineering the subsurface to manage thermodynamic output. When physical, mechanical realities are ignored, smart infrastructure shatters. To build a road that generates power, we first have to mathematically rebuild the road. We start with a blank slate. Our constraint is a single 10-centimeter thick surface panel that must survive the dynamic, rolling weight of a commercial transport truck without fracturing. Traditional continuous solid models treat materials as a single, unbroken mass. That works well for steel beams, but pavement under traffic loads fails through granular wear, microscopic pieces of aggregate grinding, sliding, and separating under pressure. To accurately map failure, we use the discrete element method, isolating 2 simulated particles, A and B, to model their contact mechanics. DEM tracks the force vectors and tangential sliding exactly where these individual spheres intersect under pressure. This central diagram shows how those individual simulated particles are then clustered together and bonded with cement. By calculating the physical limits of every individual bond, we can observe exactly how and where microscopic cracks initiate. These models scale that microsimulation up to the macroscopic level. We are now looking at simulated physical road panels constructed from thousands of these compressed digital spheres. We apply this discrete element model to 5 specific geometric test subjects: a square, a rectangle, a triangle, a regular pentagon, and a regular hexagon. By discretizing the road material into these precise geometries, we can subject them to extreme virtual loads and destroy them. The data will reveal which shape naturally resists structural failure. This maps the vertical stress distribution of the panels. The triangular panel achieves the highest ultimate capacity, but fails at stress diffusion. Sharp corners create extreme localized stress concentrations. Conversely, the regular hexagonal panel maintains a completely uniform stress field. The high symmetry of the hexagon natively diffuses the load across its entire volume. The peak compressive stress registers practically 0 localized concentration. Stress diffusion directly impacts physical displacement. These cross-sections show internal structural deformation right before failure. The hexagonal panel at the bottom registers the absolute lowest deformation, just 1.24 millimeters, demonstrating superior stiffness and coordination. But shape is only half the equation. This chart tracks the size effect. Scaling up the physical size increases bearing capacity, but severely exacerbates physical deformation, causing a mechanical thinning effect. To survive, the physical unit size must remain small. This shows how we assemble these units into a continuous surface. A square grid aligns its seams, creating a continuous straight-line path for cracks to propagate. The interlocking honeycomb splice, however, naturally disrupts these continuous stress paths.
The data proves that a high-strength design like the triangle destroys itself. The only geometry capable of surviving long-term vehicular dynamic loading is the low-strength, high-stability matrix of small-scale hexagons. With the mechanical surface geometry solved, we descend into the subgrade. Photovoltaics operating under direct sunlight create massive amounts of waste heat, but in a fully engineered system, waste heat is an asset. A road exists in a state of permanent thermal imbalance. The surface asphalt absorbs intense solar radiation, but the deep soil subgrade below the road base remains insulated and permanently cool. This naturally occurring temperature difference allows us to introduce road thermoelectric generator systems. When one side touches the hot pavement and the other a rod in the cool soil, heat flows through these alternating semiconductors. This triggers the Seebeck effect, generating a continuous electric current. Other energy harvesting designs rely on piezoelectric sensors to capture vibrations from passing tires. But vibration harvesting depends entirely on traffic volume. The thermal gradient exists purely because the road is outside. The trapped structural heat is no longer a flaw degrading the solar cells. It is the primary fuel source for a cruise control, traffic-independent power generator. To quantify the exact power we can extract from this system, we use the Seebeck voltage equation. The generated voltage is directly proportional to T1 minus T2, the temperature differential between the hot surface and the subgrade heatsink. That differential is multiplied by S, the Seebeck coefficient, which is strictly dictated by the atomic properties of the doped semiconductor material, like bismuth telluride. But voltage is just potential. To analyze true power extraction efficiency, we model the system as an electrical circuit containing the module's internal resistance and the external circuit resistance of the grid. The maximum power transfer theorem dictates a rigid constraint. To extract maximum raw power, the external resistance must perfectly equal the internal resistance. But balancing these variables triggers a physical trade-off. A circuit with equal resistances functions as a voltage divider, forcing the transducer to burn 50% of its generated voltage purely as internal heat loss. To achieve high voltage efficiency and prevent the system from overheating, the external resistance must be engineered to be at least 100 times higher than the internal resistance. We sacrifice maximum raw power to ensure system stability. Subsurface thermodynamic harvesting relies on precise electrical balancing. Maximizing output requires navigating the strict physical limits of internal resistance to maintain system stability. We can now successfully unify the mechanical shape optimization and the subgrade thermodynamics into a single cohesive architecture. At the surface, a continuous honeycomb matrix of small-scale hexagons receives dynamic traffic loads, cleanly dispersing the stress to prevent microfractures. Deep below, vertical thermal conduits act as an active heat sink, continually bleeding the waste heat off the photovoltaics and harvesting the thermal gradient to generate baseline power. For a decade, the industry attempted to build smart roads by simply dropping fragile electronics onto flat asphalt. They ignored the mechanics of aggregate wear, and they ignored the thermodynamics of an exposed surface. The next generation of transportation infrastructure requires us to stop blindly paving over electronics and instead engineer the road itself as a resilient, solid-state energy engine.